Between the orbits of Mars and Jupiter lies a vast, sparse ring of rocky and metallic debris, the asteroids, the leftover building blocks of the inner solar system. The first of them was found on the very first night of the 19th century. On the 1st of January, 1801, the Italian astronomer Giuseppe Piazzi spotted a moving point of light in a gap where a planet had long been suspected, and named it Ceres. 3 more, Pallas, Juno and Vesta, followed within 6 years, and for a time these were reckoned minor planets. In their own right, the word asteroid means star-like and reflects how they appear in a telescope, not disks but unresolved points. But the popular image of the belt as the wreckage of an exploded planet is quite wrong. The chemical diversity of the meteorites that fall from it and the sheer smallness of its total mass long ago refuted that idea. The asteroid belt is not a planet that blew apart. It is a planet that never managed to form at all, its assembly aborted, and most of its material stolen away by the gravity of Jupiter. For all its fame, the belt is mostly empty. It stretches roughly from 2 to 3 1/3 times the Earth's distance from the Sun, but the average gap between any two sizable bodies is around 1 million kilometers, so that the spacecraft which have crossed it did so without the slightest danger, and the dense, boulder-strewn hazard of the movies is pure fiction. Its total mass is tiny. All the asteroids together come to only about 4/10,000ths of the Earth's mass, a mere 3% of the mass of the Moon, and that little is remarkably top-heavy. Just 4 bodies, Ceres, Vesta, Pallas and Hygiea, hold nearly 2/3 of it, and Ceres alone accounts for almost 40%. Below these giants, the millions of smaller bodies follow the size distribution of a population ground down by endless collisions, countless small fragments, a scattering of large ones, with the smallest most numerous and the largest holding most of the mass. It is the signature of a system worn smooth over 4.5 billion years of mutual battering. Since we cannot visit them one by one, what asteroids are made of is read from the sunlight they reflect. Different minerals, olivine, pyrozine, water-bearing clays, metal absorb light at different wavelengths, leaving telltale dips in an asteroid's spectrum. From these, astronomers have built a taxonomy and 3 great families dominate it. The C-complex bodies are dark and carbon-rich, reflecting only a few % of the light that strikes them, often bearing the mark of water-altered clays. They are the most common type, and they crowd the outer belt. The S-complex bodies are brighter and stony, rich in the silicate minerals olivine and pyrozine, and they dominate the inner belt. And the X-complex bodies are spectrally featureless and ambiguous, a bland smoothness that can hide metal or primitive rock, or other materials that the early data simply could not tell apart. It is worth a caution. A spectral class describes a spectrum, not a guaranteed composition, and tying a class to a specific rock type demands more evidence than color alone, from brightness, from radar, or best of all, from a returned sample. That harder evidence comes from meteorites, for asteroids are the parent bodies of most of the rocks that fall to Earth, and a meteorite can be held and analyzed as no telescopic spectrum can. The commonest meteorites are the chondrites, undifferentiated rocks that never melted, and so preserve in tiny once molten droplets the very composition of the original solar cloud. The ordinary chondrites match the stony S-type asteroids, and a long-standing puzzle, that fresh chondrite in the laboratory looks redder and duller on the asteroid's surface, was resolved by the discovery of space weathering. The slow reddening of an airless surface by the endless sandblasting of micro-impacts and the solar wind, confirmed directly in grains brought back from one such asteroid. The dark carbonaceous chondrites, rich in water, carbon and organic molecules, match the C-complex, and are the closest analogues we have for the most primitive asteroids of all, the water-altered bodies from which, as we shall see, whole cargoes of the ingredients of life have lately been returned. Not all asteroids stayed primitive. A minority grew large enough and formed early enough to melt heated from within by the decay of a short-lived radioactive form of aluminium, and once molten, they separated like the Earth into a metal core, a rocky mantle and a crust of volcanic basalt. The timing was everything, for that radioactive aluminium decayed away within a few million years. Only bodies that assembled in the solar system's very first moments captured enough of it to melt, while later forming bodies of the same size stayed cold and unchanged. This single fact explains why the belt holds both fully igneous little worlds and pristine, never-melted rubble. The great example is Vesta, a dry, differentiated protoplanet, in effect the smallest surviving building block of a rocky planet. We know its structure in detail because we hold pieces of it. A whole clan of meteorites matched to Vesta by their chemistry were blasted off its surface by the enormous impact that scooped a 400-kilometer basin out of its south pole, a crater nearly as wide as Vesta itself. The belt is not spread evenly. In 1866, the astronomer Daniel Kirkwood noticed curious gaps in the distribution of asteroid orbits and correctly traced them to Jupiter, where an asteroid's orbital period falls into a simple whole number ratio with Jupiter's, orbiting exactly 3 times, say, for each single orbit of the giant. The planet's repeated gravitational tugs, instead of averaging away, add together in step. And over 1 million years or so they pump up the asteroid's orbit until it grows so stretched that the body crosses the path of Mars or the Earth and is flung out of the belt entirely to strike a planet or fall into the sun. These resonant gaps are the great escape hatches of the belt, the channels through which its fragments are steadily fed into the population of near-Earth asteroids. And yet not every resonance empties a region. Some shelter families of bodies instead, like the Trojans that ride 60 degrees ahead of and behind Jupiter in its own orbit, trapped and stable, sharing the giant's path around the sun. The gaps also organize the belt into zones, and those zones are compositionally layered. Cross the strong gap near the middle of the belt and the population shifts, from the stony, silicate bodies of the inner belt to the dark, carbon-rich ones that dominate the outer. This radial gradient, primitive, water-bearing material growing steadily more common with distance from the sun, is a fossil of the temperature structure of the cloud from which the solar system condensed. Close in, where it was hot, only rock and metal could solidify. Farther out, where it was cold, the volatile and organic-rich materials survived. The belt thus preserves, frozen into its arrangement, a record of the conditions under which the planets were born and layered over it, the fingerprints of a later, violent mixing that carried icy bodies inward from beyond. To read the belt across its width is to read the chemistry of the young solar system from the inside out. Superimposed on this smooth structure are tight clusters of asteroids sharing almost identical orbits, and in 1918 the Japanese astronomer Kiyotsugu Hirayama recognized what they were: the shattered fragments of common parent bodies, broken apart by collisions and still traveling together. He named the first few. Today, well over 100 such families are known. They form in 2 ways: a glancing blow that cracks off a swarm of fragments while leaving the parent intact, as at Vesta, or a catastrophic smash that disperses an entire body. A crucial lesson emerged from modeling these events. Most of the larger fragments are not solid shards of the original rock at all, but loose piles of rubble, gravitationally regathered from the debris of the collision. This is why so many asteroids, including every one yet visited by a spacecraft, turn out to be not monoliths, but rubble piles, heaps of gravel and boulders held together by little more than their own feeble gravity. And because a family's fragments were all born in the same instant, the slow spreading of their orbits over time serves as a clock, letting astronomers date the collision that made them. A handful of asteroids are large enough to have had geological lives of their own, and a single NASA spacecraft, Dawn, the first ever to orbit 2 different worlds beyond the Earth, transformed our knowledge of the 2 greatest. Ceres, 940 kilometers across and the largest body in the belt, proved to be no dead rock but a partially differentiated, water-rich world, its rocky interior wrapped in a layer thick with ice, salts and clays, massive enough indeed for its gravity to have pulled it into a sphere, making it the inner solar system's only dwarf planet. Its most startling features are the brilliant white deposits gleaming from the floor of one great crater, identified as salts left behind by briny water that welled up from a reservoir tens of kilometers down and evaporated at the surface, deposits so young that Ceres may still, even now, be faintly active, oozing brine from within. Ceres blurs the very line between an asteroid and an icy ocean world. Vesta is Ceres' opposite in almost every respect. Not a wet, primitive dwarf but a dry, fully differentiated igneous protoplanet, 500 kilometers across, with a metal core and a basalt crust, a fragment of the earliest planet building, frozen at the moment of its making. Dawn confirmed everything the Vesta meteorites had implied, mapping the towering South Polar Basin whose excavation had flung those very meteorites toward Earth, and finding laid bare in its depths the deep crustal rock the impact had dug out. Between them, the 2 worlds Dawn visited capture the belt's whole range: Ceres the icy, water-altered, possibly still living body, and Vesta the dry, once molten, long-dead protoplanet, the 2 poles between which the belt's millions of lesser bodies are strung. A third kind of large body has drawn a mission of its own. Scattered through the belt are the metallic asteroids, rich in nickel and iron, and the greatest of them, called Psyche, is some 280 kilometers across. Its nature is one of the belt's genuine open questions. It may be the exposed metal core of a small planet whose rocky shell was stripped away by ancient collisions, in which case it would offer humanity its only conceivable access to the kind of material that lies forever unreachable at the center of the Earth, or it may be a body that simply formed unusually rich in metal, never fully differentiated. To find out, NASA launched a spacecraft, also named Psyche, in October 2023. It will reach the asteroid in 2029, and only then will we learn which of these two very different stories is true. Until it arrives, every confident claim about Psyche as metal and its origin should be treated as a hypothesis awaiting its test. Why is the belt so nearly empty, and why are the orbits of its survivors so stirred up? These are among the liveliest questions in planetary science. The clue is the missing mass. Had the region between Mars and Jupiter kept the same density of material as the zones where the rocky planets formed, the primordial belt would have held perhaps an Earth's mass or more, 1,000 times what remains, and would surely have grown a planet of its own. Instead, some 99.9% of it is gone, and the little that survives is dynamically hot, its orbits far more tilted and elongated than the near-circular paths in which bodies are born. Any good theory must both empty the belt and stir it. One leading idea, the grand tack, has the young Jupiter migrate inward toward the Sun, and then, once Saturn formed, turn and sweep back out again, a two-way passage that scattered and depleted the primordial belt, truncated the disk to explain why Mars is so small, and on its return, seeded the outer belt with dark, carbon-rich bodies flung in from beyond the frost line. The grand tack is not the only story. A rival class of models proposes that the belt was born nearly empty, and that almost all its present bodies, the stony and the carbonaceous alike, were implanted from elsewhere as the giant planets grew and shifted. A third holds that a moderately unruly Jupiter could have stirred and thinned a locally formed belt without any grand migration at all. And a later upheaval, a dynamical reshuffling of the giant planets, long after their birth, is invoked to explain a further round of erosion and the injection of the reddest, most primitive bodies of all, drifting in from the distant edges of the system. What is robust across all these accounts is the qualitative picture, a sparse, stirred-up relic, its mass cut by a factor of 1,000 and its composition, reflecting both where things condensed and what was later carried inward. But the precise sequence of migrations and instabilities that produced the belt we see remains genuinely unsettled, and any single, confident narrative should be read with that uncertainty firmly in mind. For the smaller asteroids, a force far subtler than any planet's gravity quietly reshapes their fate, the gentle push of sunlight itself. An asteroid warmed by the sun does not radiate that heat back instantly. Its rotation carries the warm afternoon side around before it glows away its heat into space, and because that escaping heat carries a whisper of momentum, it acts as a continuous feather-light thrust. Over millions of years, this Yarkovsky effect can nudge a kilometer-sized asteroid inward or outward by a substantial fraction of the belt's width, enough, crucially, to deliver it into one of Jupiter's resonant escape hatches, which then flings it toward the Earth. It is this slow radiation drift that keeps the near-Earth population supplied. The effect has been measured directly on the asteroid Bennu, whose orbit shifts by a fraction of a kilometer each century. And that tiny, well-measured drift is the largest single uncertainty in projecting Bennu's small but real chance of striking the Earth 2 centuries from now. A cousin of that effect works not on the orbit but on the spin. When sunlight falls on an irregularly shaped asteroid and is re-radiated unevenly, it exerts a tiny torque, and over ages this can spin the body up or slow it down. The spin-up is dramatic for the rubble pile asteroids that make up most of the small body population, for as such a loose heap is driven faster and faster, toward a spin so quick that a strengthless pile would fly apart, it begins to shed material from its bulging equator. This is thought to build the strange spinning top shape, a bulging equatorial ridge, like a child's toy, that spacecraft have found at more than one asteroid, and even to fling off enough debris to spawn a small moon or to split the asteroid into a pair of bodies traveling on neighboring orbits. These featherweight forces of sunlight, utterly negligible on the scale of planets, turn out to be first-order sculptors of the small asteroids, of their orbits, their shapes, their spins, and their companions. Those asteroids driven out of the belt and onto orbits that approach the Earth are the near-Earth asteroids, and they are watched with particular care, for a reason both scientific and existential. They are short-lived wanderers, surviving only a few million years before they strike a planet, fall into the sun, or are flung away, so the population must be constantly renewed from the belt. Astronomers sort them by their orbits. Some circle entirely inside the Earth's path, some entirely outside it, and some cross it, in a taxonomy of subtly different classes. The ones that matter most are the potentially hazardous asteroids, those large enough and passing close enough to threaten regional devastation should they ever strike. A body of roughly 140 meters or more, whose orbit brings it within a fraction of the Earth's distance from our own. Tracking these is not an academic exercise. It is the first line of a genuine planetary defense. That defense begins with finding them, and dedicated survey telescopes now sweep the sky night after night, their catalogues swelling past 38,000 known near-Earth asteroids. The largest, the roughly 900 bodies a kilometer or more across, any of which could end a civilization, are now more than 9/10 accounted for, and none of them threatens us. But the smaller, still dangerous population of 140-meter bodies is only partly found, and it is to complete that census that a dedicated infrared space telescope is being built. The difficulty is that a dark asteroid seen only as a point of light betrays its size ambiguously. The same brightness could be a smaller, shinier rock or a larger, darker one, so estimates of how big, and therefore how dangerous, a newfound object is remain uncertain until it can be studied more closely. The catalogue grows, the completeness climbs, and with each survey the odds of being taken wholly by surprise shrink a little further, and for the first time in history, we have shown we can do something about it. On the 26th of September, 2022, a NASA spacecraft called DART deliberately flew into a small asteroid, a 160-meter moonlet orbiting a larger one at some 6 kilometers a second, in the first real test of deflecting an asteroid by force. The pairing was chosen deliberately, for the little moon's orbit around its partner could be timed precisely from the Earth, and the result was measured with confidence. The impact shortened that orbit by about 32 minutes, far more than the mission needed to count as a success. And tellingly, the deflection was far larger than the spacecraft's own momentum could account for, because the strike blew out a great plume of debris, and the recoil of that ejected material amplified the push. A European spacecraft is now on its way to survey the crater and weigh the moonlet, and so turn a one-off demonstration into a calibrated, repeatable technique for nudging a dangerous asteroid off a collision course. The hazard these efforts guard against is real, but it is graded steeply by size. The bigger the impactor, the rarer the strike. Meter-sized, rocks hit daily and burn up unseen. The truly civilization-threatening bodies arrive only across hundreds of thousands of years. Two events within living memory mark the dangerous middle ground. In 1908, an object perhaps 50 meters across exploded in the air over Tunguska in Siberia with the force of many megatons, flattening some 2,000 square kilometers of forest, the largest impact in recorded history, and it left no crater, for it burst before it reached the ground. And in 2013, a body only about 20 meters wide, entirely undetected, streaked in over the Russian city of Chelyabinsk and burst high in the sky. Its shock wave shattered windows across the region and injured over 1,000 people. That a rock too small to have been on any watch list, arriving out of the daytime glare, could still hurt a city is precisely why the surveys press on, and why astronomers use a simple scale, running from 0 to 10, to communicate the risk of each new object to a public prone to alarm. For all that telescopes and flybys can tell us, the actual makeup of a primitive asteroid stayed uncertain, until 2 missions went and fetched some. Japan's Hayabusa2 reached a dark, spinning-top asteroid named Ryugu, touched down twice to snatch samples, even firing a projectile to blast a fresh crater and gather the material beneath, and parachuted its capsule back to the Australian desert in 2020 with 5 grams of pristine asteroid, many times its design target. And NASA OSIRIS-REx visited an such body, Bennu, and returned to the Utah desert in 2023 with 120 grams of it, the largest sample of a carbon-rich asteroid ever brought to Earth. These were, in effect, the first proof that a spacecraft can rendezvous with a tumbling rubble pile, work at its surface in near weightlessness, seize a piece of it and carry it home, the very skills any future asteroid venture, scientific or commercial, would need. And the treasure they brought back has been extraordinary. For when the returned grains of Ryugu and Bennu were opened in the laboratory, they proved to be laden with the chemistry of life. Both carried water-altered clays and a rich inventory of organic molecules. Bennu, the richer of the two, held ammonia, nearly 100 distinct amino acids, among them 14 of the 20 that build the proteins of every living thing on Earth, and, astonishingly, all 5 of the nucleobases that spell out the genetic code of DNA and RNA, together with the sugars and phosphates that life requires. The message is profound. The molecular building blocks of life were assembled, without any life at all, in the cold water of primitive asteroids at the very dawn of the solar system, and were delivered to the young Earth by exactly this kind of body. It is not evidence of life. The great mystery of how such molecules first crossed into living things remains wide open, but it is evidence that the ingredients were everywhere. Asteroids are often spoken of, too, as the mines and waterwells of a coming space economy, and the geology behind that dream is real, even if the economics remain speculative and unproven. But the surest treasure the asteroids hold is not any imagined fortune in metal. It is the record, written in their orbits, their spectra, and the pristine grains we have at last begun to bring home, of how our world was built, and of how the stuff of life was scattered, from the very beginning, across the sky.